Okay, we're going to start stoichiometry, and I promise the hardest part of stoichiometry is the word stoichiometry. So if you can spell that, then you should be good to go. As long as you label your units on everything, like I've really been emphasizing, you should be good to go. So refer to this as the cheeseburger problem because we're going to use an analogy of the perfect cheeseburger recipe. We're going to go much more into detail on this in class, but just to give you an idea, a recipe, this is my recipe: 1 hamburger bun, 2 patties, 2 slices of cheese, and 4 strips of bacon. And if I have that ratio of all of those things, I can make the perfect cheeseburger. If I only have 1 slice of cheese, I am unable to make this recipe. If I have 10 buns, 20 patties, 20 slices of cheese, and 40 strips of bacon, I can make 10 times this recipe. And so this idea of looking at a recipe is analogous to looking at a chemical recipe. Okay, so if you see, I need all of these things to make 1 cheeseburger. So 1 plus 2 plus 2 plus 4 equals 1. And we know that it doesn't work math-wise, but that makes sense to us, that we can put 9 things together and make 1 thing. Well, chemical recipes work the same way. I need 2 of these and 1 of these, and it doesn't make 3, it makes 2 of those. Or if I look at another recipe, I need 1 of these and 2 of these to make 1 of these and 2 of these. Okay, so it's not a perfect math situation, where we look at it as a math problem. 2 plus 1 should equal 3, and it doesn't because of the way things combine. And that's the same way we look at a recipe. So how does this all relate? Well, the coefficients in the chemical equation represents number of molecules and not the mass of the molecules. Or it represents moles. Okay, it doesn't represent grams. So I don't ever look at a recipe like I have for my cheeseburger and say that I need 1 gram, 2 grams, 2 grams, and 4 grams. It doesn't work that way. We look at it as an amount, and that's going to be the same way we do here. And we're going to explore this deeper in class, this analogy. But we don't want to count molecules for our chemical reactions. I don't want to go and count that I need 25 sodiums. That doesn't make sense. Sodium is so small that wouldn't work. And so we're going to count things by weighing. So in order to know how many, grams of something, how many molecules of something I have to look at how many grams I have. And when we have different atomic masses, how can we compare the compounds? Well, how does this work? If I have things that weigh this many grams, 25 grams, and this weighs 50 grams, and this weighs 137 grams, if I look at all my different elements, how can I compare? Well, this is where moles comes in, and that's why we just finished mole conversions. And so looking at a problem, we have a series of steps. So a problem will look like this. It'll say, if 12.5 grams of C4H10 are burned in air, how many grams of carbon dioxide is formed? And that's the type of question you'll solve. There's 5 steps that you need to go through with any question. Sometimes I give you some of the steps, sometimes I don't. The first one is you need to write a balanced equation for the reaction. It's not any good if the reaction is not balanced. And so you need to have a balanced reaction. And so this is why our formula writing, our polyatomics, our balancing and writing equations, all of these steps are now going to culminate in this stoichiometry. So if any of those are weak, you need to see me to make sure that we understand how to write a formula, how to write an equation, how to balance an equation, how to predict products. The second step is we need to convert the known mass of the reaction or product, can work either direction, to the moles of that substance. So I can sometimes talk about a product and figure out how much reactant I had, or I can talk about a reactant and figure out how much product. Or I can talk about a reactant and figure out how much more other reactant I need. Or I can talk about a product and figure out how much of another product. It works anywhere in the equation. 3, use the balanced equation to set up the appropriate mole ratios. So I want to see what my mole ratio is. That's my recipe. That's where the recipe analogy comes in. I need to use the mole ratios to calculate the number of moles of reactant or product. And so this mole ratio, we looked at this in lab. We looked to see what our mole ratio was, and this is going to become an important part of the calculation. And 5, we're going to convert from moles back to grams if required by the problem. Okay, so these are our 5 steps for any stoichiometry problem. They're going to become pretty inherent, so it's not that you're going to list and write down these steps, but some people really need to see it sort of spelled out so they know what to do, so I wanted to do that for you. So here's our problem again. It says if 12.5 grams are burned in air, how many grams of carbon dioxide is formed? Well, our first thing told us that we needed a balanced reaction. So I'm going to start with C4H10. It's burned in air, that means I'm adding O2. And it's burned, so it's a combustion reaction. And I know that all of my combustion reactions produce CO2 plus H2O. When I go to balance this, I notice that if I go ahead, that I have 10 H's, and if I put a 5 here, that's going to give me 5 oxygens, which is an odd number. So I've done enough balancing to already know and recognize that I need to double this. If you didn't recognize it, you would have ended up balancing it, and then you would have been stuck with a 13, what times 2 equals 13. So I'm going to just get us to this point. So then I have 8 carbons, so I need 8 carbons. I have 2 times 10, I have 20 hydrogens, so I'm going to put a 10 here. And then I have 10 plus 16, so I have 26, which means I have 13 O2s. Okay, so I have a balanced reaction, and now that's useful. I always set up my questions like this. 12.5 grams is what I have. How many grams of carbon dioxide? Question mark grams. Now I know what my problem is, and I can not look back at the words anymore because I have it spelled out there. I'm always going to take what I'm started with. I'm going to start with 12.5 grams, and this is where this labeling becomes so key. I've been so picky about this, and this is why. Stoichiometry problems are 3-step problems. And so by being 3-step problems, I can go ahead and say 1, 2, 3, and then equals. I don't want grams of C4H10, so I'm going to put it on the bottom. And actually, I do want grams of CO2, so I know that's going to be my final answer. In order to compare this, the only way I can compare my C4H10 and my CO2 is with moles. So I need to convert this to moles. I don't really want moles of C4H10. I ultimately want moles of CO2. And there's a special part here in the middle that I like to refer to as the big switch. And this is the one place in the problem where I'm going to get rid of moles of C4H10 and I'm going to convert it to moles of CO2. This is where that mole ratio comes into play that we learned about in class. I really don't want moles of CO2. I really want grams of CO2. So I'm going to put grams of CO2 on the top. And then my answer is grams of CO2. Look at all of that labeling, all of those units that are in there, and I haven't even put a number in. This is the best way to set this up because then I'm sure to be right. I know that other than this big switch that I have here in blue where I have moles over moles, anytime I have moles and grams, that number is 1. And then for my grams, I know that that's the gram formula weight. So the gram formula weight here happens to be 58.14. And the gram formula weight happens to be 44.01. In this big switch part here, let me grab another color, I'm going to go back to my balanced chemical equation and look at my mole ratio. I'm going to write in from the balanced equation that I have 8 moles of CO2 to 2 moles of C4H10. I don't reduce it. Would it work if I did? Of course it would. It's multiplying and dividing. But there's no need to. I want to go ahead and take this 8 and this 2 and plug it right in there. And that only happens in this middle step. Now I can go ahead and multiply. 12.5 times 1 times 8 times 44. I'm going to divide that by 58.14 times 2, and I solve this problem and I get 37.9 grams of CO2. And that's my problem. So I have now followed all 5 steps here. Okay, I wrote a good balanced equation. I converted the mass of the reactant or product, happens to be reactant, to moles. So here's my grams to moles. I used the balance equation to set up the appropriate mole ratio. There's my mole ratio in that big switch. Okay, we can call it the big switch because that's where we're switching chemicals. I can use the mole ratios to calculate the number of moles to calculate it, and then I can convert back to grams. Now, we know how to do particles and liters and all that good stuff. So if I started with liters, I could put liters here and just do, it's always 3 steps. And if I wanted to solve for liters, instead of putting grams here, I would have put 22.4 liters, and that would have given me the answer. So my liters and particles are all also interchangeable in here. Let's take a look at one more example. So silver nitrate plus potassium bromide. So here I've given you the equation. You always need to check and see if it's balanced. Okay, my silver's balanced, my nitrate's balanced, potassium, bromine, it's all balanced. 64.18 grams of silver bromide. I'm going to put it above it since I formed from how many grams of silver nitrate? Question mark grams. Okay, so I'll go back to my red that I was using. So now I'm going to start with what I'm given, 64.18 grams of AgBr. I'm going to put my 3 steps down. I want to get rid of grams of AgBr. What do I want to convert to? Of course, it's moles of AgBr. I want to get rid of moles of AgBr. I'm ultimately trying to get to AgNO3. So moles of AgBr goes down here, and moles of AgNO3 goes on top. What is that referred to? What is this special section here? This is my what? My big switch. And where am I going to get those numbers from? Where am I going to get these moles from? My balanced equation happens to be 1 to 1. And I'm just going to go ahead and fill it in because I'm talking about it right now. So 1 to 1 happens to be, and that came from here. 1 is here, and 1 is here. And then I really don't want moles of AgNO3. I want grams of AgNO3. These moles always are 1 because moles and grams are always 1. This happens to be 187.77 for the gram formula weight. This happens to be 169.88 grams. I'm going to multiply across. I'm going to end up dividing. I end up with 58.07 grams of AgNO3. And that's my answer. That right there is stoichiometry.